I can talk about the interaction curves for, yeah. You know, I will wrap it up fairly quickly and then, yeah, plenty of time. So these are given. So we're talking about the P delta effect for a column, 24 by 24. That's what we got, if you remember, right? So now I have a size of the column. I have the P values and the moment values. The question is, will the 24 one will satisfy those numbers I gave you in the earlier slide? What is the number I need? I need to make sure whether or not this is going to satisfy the design. Right? That's how it goes.
Yes.
Okay, good. So we have all these are given to you. 3 of number 8 bars at the top and bottom, meaning the compression and tension side, and then with a cover, the clear cover of 1.5 inches, the tie diameter is ½ inch, the half diameter of 1 inch is ½ inch, so the cover is 2.5 inches total. Clear cover is different from cover, right?
Yes.
Okay, good. Now we are trying to design. So what is the thing we learned? Very fundamental first thing. We are assuming that. The most important, right? That is 60 KSI. In this case, or maybe in this case, it is 65 KSI because I used 6.5 million PSI as my stiffness. So you don't get 60 KSI, it is 65 KSI, right? Okay. So compute the interaction curve. I'm trying to find how that interaction curve goes for different C values, right? So if it is a compression failure mode, how many times I told you yesterday? If it's a compression failure mode, this is the neutral axis. So if it is a compression failure mode, it will be like that, right? For say C is 4, C is 12, it will be like my strain in the concrete increases and increases. It did not reach 0.003, and this is less than 0.1. So it went, my C value increased, whatever that. Now if I go to 22 inches, it went up, right? So the C value increased. That's what we are talking. Like that. Okay. In any compression mode, as you increase the load, the C value goes up. Compression mode, not tension mode. Okay, that's what we are trying to find out. If that is the case, as the C value increases, my bending effect up to a point also increases. That's what we'll see, how much that increase is. So again, my limitations are two-folded. One is I cannot exceed 0.1. Another is this.
Yes.
Yeah, those are, I cannot exceed both. So what I have done based upon the strain compatibility, see this strain compatibility, that is the strain compatibility equation, right?
Yes.
From that, what is the strain at 4 inches, epsilon C at 13 inches. These are just some random numbers I picked. And at failure, typically at failure, C value is close to the tension reinforcement. Typically, it's very close. If not, the tension reinforcement becomes compression reinforcement at a high eccentricity values. Meaning what? Meaning that almost near failure. Almost near failure. I'm saying near failure. My neutral axis. I didn't write right. My neutral axis is going to be like that. Near failure. So my reinforcement at a high C value could jolly well be in compression. Now I'm going to try to find out. So using this same strain compatibility, I don't have to repeat it over and over. You see that? Using this same strain compatibility equations, I'm going to determine for different eccentricities of load, what is the strain in the FRP in tension. Very, very low, you can see the tension strain values. Again, this is all from the strain compatibility. Please look at here. Again, we can see, you remember that those numbers, the C, and this is the modulus of FRP. You recall the strain compatibility equation? Good, good. So that's what I got. If the strain in GFRP is negative, the GFRP stress is set to be 0, meaning we are again saying GFRP does not take any compression strain, but that only happens at extreme values, okay? It may not even happen.
Yes.
But if at all it happens for a very high C value.
Sir, what's the significance of the numbers?
I'm going to come.
Strain compatibility equation.
Right. Okay.
For C at 4.
For different C values, I have different strain values. That's all it means. Now, next slide, I will show you how that translates to how much moment capacity that section will have corresponding to different C values.
Not that, sir. In the first, at C is equal to 4 inches. We have taken the first term as 0.0023. But in the second and the third, it's 0.003.
No. 0.003 is my limit.
Yes, sir.
Okay. At 4 inches, my strain in concrete is 0.023.
Yes, sir.
At 13 inches, the strain in concrete is 0.15. Okay. Likewise at 22 inches. So what this implies is, can you read that? But I can have any high strain I want. It has no meaning to it once it exceeds. That's what it means.
In the second step, sir.
Okay.
For GFRP.
Okay. For GFRP, corresponding to the strain compatibility equation, for this strain, I have
This much of strain.
These are the strains in tension. These are the strains of GFRP
In compression.
in compression, but that doesn't matter because we are assuming it same as that of concrete. You know, we are not
At compression.
in the compression side.
Yes.
That's what it means. Now, we are going to use these numbers to see how, if the strain in GFRP is negative, GFRP stress is taken as 0. In other words, you don't multiply this with 6.5 million PSI.
Sir, why did we take 0.003 at C is equals to 13 inches?
No, we are not taking any, this is my limit.
GFRP, sir.
Oh,
Down, sir.
okay.
The second last.
The second one.
Yes, sir. The first term is 0.003. Here, sir. At C is equal to here.
Okay,
That
good.
is 0.003.
Okay. You recall the strain compatibility relationship? Please note, it's very, very high, but it is limited to 0.03 for 13 and 22. That's why.
0.003.
That's right. Relate this to strain compatibility, wherein my limit in terms of strain in concrete is 0.03. I mean, theoretically, I can get a high value. It has no meaning because it already cracked. Find the corresponding stresses. For 4 inches, my stress is 0.01. And in concrete, it is that which is taken as 0, right?
Yes.
For 13 inches, it went up, or whatever, 13 KSI, and still 0 for concrete. For 22, what does this mean?
Negative.
Negative mean. So it is not in tension. I told you earlier, for a very high C value, you could get into compression, meaning the neutral axis is below. I drew it here, right there. Neutral axis is below this level. So that is for this case. Sometimes it may not go below that,
Yes.
depending on the dimensions, depending on the area of this GFRP and all other things.
Take the limiting case where the maximum compressive strain is 0.003, not beyond that.
That's correct. It's never.
But in the previous slide, I think it has exceeded 0.003 at C equal to 20.
You could, in theory, you are exceeding, but as a column, it knows it cannot take any more than that. If I use the classic strain compatibility relationship, I'm exceeding. But that doesn't mean anything. For example, okay, let's talk about, for half a minute, let's look at stress versus strain of steel. Right?
Yes.
It is like this. Right? This value is 002. Right? 02 or 002. 30 or 60 divided by 30. 10 to the 3 by 10 to the 6. So it is 2 times 10 to the minus 3. That is 002. Correct?
Yes.
Okay, good. Now, sir, my strain has exceeded, I'm here. Means I have 004 or 008, whatever. My yield value is still 60, whether I'm here at 002 or I'm at 008, it is still 60. That's what we are talking. My stress does not exceed, my strain does exceed, doesn't matter, beyond a point. Huh? This is not steel, this is a GFRP column. No, I'm just using that as an explanation for you What happens when you go beyond 003 is still the same effect as if it is 003. And that is the explanation I'm giving you.
But 003 is that of the concrete. Concrete will fail after that.
Of course it fails after that. Okay. You have concrete, this is. We are limiting it. We are limiting it to, it may go something like that, but we are limiting our analysis to 003 from a strain point of view. It failed already, you see. All right?
Yes, sir.
So, from the force equilibrium, okay, what do we have? From the force equilibrium, this is a 5000 psi concrete. Beta 1 is not 0.85, beta 1 is 0.8. That's the ACI code. You remember yesterday I gave you how beta varies by per thousand it's 0.05 reduction.
Yes, sir.
So from 0.85 for 5000 it's 0.8. For 6000 it's 0.75, like that. Okay. So now let's construct the force equilibrium. What is the force equilibrium? That is our PN curve. This is, first term is the amount of force resisted by concrete in compression minus or plus the force resisted by FRP. I said minus, wait, that's what I'm trying to say. It is minus if FRP is in tension, it is plus, it is in compression. That is what we are trying to say. So this is the, for 4-inch, that is the biggest contribution, and this is what we have already computed. Please note, in the earlier slide, where did I get this from? The earlier slide. It's 172. The PN value for 13 inches is 1027.
Here we did not minus because it crossed the...
Here it crossed, exactly right. You remember I said we exceeded the 22 inches, the neutral axis. Therefore, it went into the compression zone. Therefore, we are not accounting for that. That's the point. Good catch. Good catch. Then I multiply that with our phi factor, effective, and that is the maximum value. And likewise now I'm doing exactly the same thing. I'm picking up the p-values, correspondingly multiplying with the lever arm values. Look at the lever arms, please. That is the lever arm for concrete. That is the lever arm for FRP. Why is it plus? One is tension, the other is compression. When you look at, take the moments about the neutral axis, what happens? You get the same clockwise moment or a counterclockwise moment till such time it goes below
22.
That's right. That's right. But we are taking it as 0 anyway.
Yes.
So it didn't matter. So that is how, of course, you use the appropriate p factors. That's how we arrived at it. Okay? Very elaborate, a bit too involved, but it works.
What to find the...
This is, what is this, what does this interaction curve tell us? Now you go back in terms of what this column is subjected to in terms of applied loads, with proper load factors. You remember I said combination 2 and 3? So whether or not the loads or the moments that are induced by the combination 2 or 3 are those moments higher than the ones I gave you here. If they are higher, then I'm in trouble. I have to redo it. If they are lower, coming from the applied loads, then I'm in good shape. So that essentially concludes how you check whether your column is satisfactory or not. So this is a computationally heavily involved, but if you computerize it, there's no problem.
Sir, to get the point of maximum moment, can we equate like the strain of concrete will be equal to the strain in FRP at failure?
You see, that's what I was telling when this man was here. Yes, that is a correct answer, provided we are dealing with steel. That is unfortunately not the answer with FRP, only because our 0.01, we kind of fixed it as a balanced value, right?
Yes.
Which is not necessarily, I don't want to use the word correct, I want to say
Properly interpreted.
it is typically more of the order of 0.015 to 18. Therefore, you will get a much higher value in reality after you do the test than what you're seeing here. That's why I don't want to use the way you. I would have said yes, yes, yes. If my FRP, see here for steel, I can never ever exceed the 60 KSI.
Yes, sir.
And then I could have said what you said, because that's the balanced case, that is the maximum case. But with FRP, even though I'm using 60 or 65 KSI, in reality I'm going much higher, almost, not quite, at least 50% higher, if not 100% higher. Therefore, I cannot say what you are wanting me to say. No.
What should do?
No, this is a lower bound case. Remember, we are in a design business, not in an analysis business. All this will be telling you is a lower bound. You are safe. Now, if you want to optimize your design, you don't want to spend extra money on your extra FRP bars, then you have to justify it. No, I am taking it as not 0.01, I'm taking minus 0.015 or 0.02, then run the analysis. Why am I taking? Somebody is going to ask you. I've done 55 tests, I'm always getting 0.02. That's how you, so the code, I said this before, the code permits you to do that. Remember, the code is a lower bound code. It is not an upper bound code. That's always, and the code asks you, you challenge us. You see, they are not worried, they're always looking for the right answer. They have no ego here, I'm right, I'm wrong, no. So, but we guarantee you that what you're getting is a lower bound. That we guarantee. From a legal point of view, it's always guaranteed. What is guaranteed? Lower bound, not the accuracy of it.
Yes.
Right? Okay, that's it.
Sir, my exact question was how to determine the peak value.
I know, but there is really, if you have patience, all you have to do is don't take, okay, look here. If you have patience, don't jump from 4 inches to 13 inches to 22 inches. Okay, we know the peak value is somewhere around 13 inches. So keep going to 13.5 or 12.5 or 14 and compute the number. All right, that is a sledgehammer technique,
Yes.
right? But what is it we call it? In US we call it, we are trying to shoot a mosquito with an elephant gun. That's what that is. But a more sophisticated approach is you can program it, you get a third order equation, you can solve it, you get an exact number from that. But nowadays, people are confused between what is second order and this third order. Therefore, I don't know in this country, in US, we are having a problem with students being exposed and employing hardcore mathematics. The students just want to, with the advent of computers, our attention span has come down because you have to always look at this stupid iPhone every 15 minutes. I don't even know why you want to look at the iPhone, but that's a habit, not that it is giving you anything. Nothing is going to fall apart if you wait for 3 hours, right? But I look at it. Why? It's a habit, So with that, what is the downside of it? You don't have an attention span. When I keep talking, you're thinking somewhere else, you see. That's a separate topic. But you can find, quote unquote, an exact solution by coming up with a closed form third degree polynomial.
The equation of the curve.
That's right. And do we care? We don't. As a designer, I don't care. As long as I'm within 3-4%, I'm happy. You know what I mean?
Yes, sir.
As a designer, As a mathematician, is a different topic. But so, my last example, at least I will introduce the theory, then I'll run the example tomorrow along with fire presentation. I'll do that tomorrow on fire. But at least let me introduce the theoretical part before I run the computations, which will be done tomorrow. So, what is the theory telling us? Okay, first of all, what is this two-way slab? What is that? I already introduced to you. It is a plate bending type issue, and your del square equation for the moment, it becomes a del 4 equation for the deflection. Same as your beam bending equation, right?
Yes, sir.
D square y dx square is mx over ei, or d4y over dx4 is qx over ei, right? You remember that?
Yes.
So it's essentially the same thing, but here suddenly I have two independent variables, not one independent variable. If it is a one independent variable like in a beam, we call that in the horizontal axis, that is called an ordinary differential equation. With a two independent or more variable, that becomes a partial differential equation. If I am going to modify my differential equation to, if I keep modifying that, then that is called a partial differential equation of variable coefficients. But we are not dealing with that. That's a composite. That's an isotropic material. We're not getting there. All we are getting there, we are still dealing with an isotropic material that is subjected to. So this morning I told you, if I have two beams, I'm talking about deflection on the long side, deflection on the short side, and that is, you remember that your good old 5/384 WL4 over, that's essentially, you remember that one?
Yes, sir.
Okay, good. I did not, I didn't show the what I call the coefficient, because that's a constant, for mathematics. That's just same thing for all different cases. I didn't show that. Okay. So by now, as a designer, you all know that we are dealing with a frame that is in the short direction, not in the long direction, right? If that frame happens to be relatively close to 1, as I said, 0.5 to 2, then you design it as a plate, a two-dimensional frame. That's what we are going to do. Or else it'll be designed typically. So most of you design a building as a two-dimensional frame, not as a three-dimensional frame.
Yes.
So why I gave that pitch is because the short span takes a larger load, generate higher moments. That is why I made that statement. So some guy, I'm not going to say a whole lot about who, what, where. Some guy introduced, he said, "Sir, you come to I designed this building, Then he has the columns oriented, rectangular columns, not circular columns. The long, like B over D, so the D part oriented it on the long side as opposed to this short side. I didn't want to say anything, but I certainly said to myself in my mind, holy cow, what did you do here, So that is why I put that statement. So
we give a point to 1 rather than DB.
it is, see, you have short side direction is what is going to drive the design of a frame, not the long side. Okay. We can use short and long side type stuff to make the design more efficient. But on the other hand, if that long short side ratio is more than 2, you are primarily depending on the short side frame, not the long side frame. I don't know whether I'm conveying my message or not. When I look at your faces, some are looking blank, therefore I'm going to say this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. These are the columns, right?
Yes.
These are the columns, correct? Ah, come on. So, do you design a frame in this direction, or do you design a frame in that direction? The answer is you design a frame in that direction. When you're designing a frame in that direction, are you going to have your column, rectangular column cross-section that way, or are you going to have a rectangular column cross-section that way? That's what we are talking about. That is, I'm saying, for a frame that's higher than a ratio of 2, of aspect ratio. That's what we are talking about. So anyway, that is what this statement implies. So in addition to that, the deflection is dependent largely on flexibility of slab supports, which is beams.
Yes.
Both beams, longitudinal beams and transverse beams. This beam and this beams, both. So never ever make a mistake of designing a frame by taking this. You always design it, if you want to design it as a two-dimensional frame. Okay. The third statement, since slabs are under-reinforced, redistribution of M takes place after. You know what that means? What does that mean? What does the third bullet mean? It means that I have a redistribution, I have a distribution to begin with of the moments corresponding to column, beam, both transverse, longitudinal, and the slab, right? If my concrete column or a beam or a slab does not crack, I am going to have fantastic elastic analysis working perfectly. Whereas if that beam or that slab or that column cracks, what happens? Moment gets redistributed. Where would it go? Obviously, it goes to locations where you have higher stiffness, you know. In a tug of war, what happened? The weak guy doesn't pull as much as the strong guy does. So ultimately, the strong guy gets to hold on to the field, right? Same thing here. At least the strong guy will attempt to hold on to it till such time he can hold it, or else he will give up, right? So same analogy here. Do you get it? That's what we are talking about. That's the last one. So redistribution takes place. In the tug of war, I don't know how many of you participated, everybody carries same pull up to a point, The weak guys, after a point, cannot pull any more than they were. So the strong guys take over. Even that is what is called redistribution. Same here. Same here. Higher the EI value, higher the attraction of the moment. So we have two methods known as direct design method, and in that direct design method, that's an ACI approach, evaluate and distribute the moment in a two-way slab panel using moment coefficient, that they define those moment coefficients for you. They're not letting you use whatever you want to use, because you'll end up making a mistake. So they define that for you. You can do it using finite element, no doubt. Then you can take advantage of it and challenge what they provided you with, which are obviously going to be on the conservative side, which means they're a little bit higher than what the FE analysis provides you with. All right. So if you look at it, what am I showing you there? What I'm showing you there is how we assume the load is distributed. That's how we're going to assume, rightly or wrongly. But this leads to eventually a crack. At failure, we are not talking about it at the service level, at failure, you're going to have a crack. And obviously, that crack initiates at the geometric center of that slab. Then it will start to extend. Okay, what is that? Let me back. Oops, sorry. So, if I take this as my slab because of the columns, because of the beams, if I take this as a unit, or if I take this as a unit, the crack starts there. And initially it will grow like that. But a point will come, this is what is called redistribution. A point will come, that crack will not go here. It will go there, that crack will go here, like that. That is called yield line theory. Post-cracking phenomenon is what you see. You follow?
Yes.
That is the basis on which the direct design method is, when the yield line theory was developed back in 1930s. Almost, not quite, 100 years ago. Okay, it still works. There are other theories, better theories, but that, so what is the equivalent width here? Common sense. What is the common sense? Center to center distance, See, design is a common sense. That is the beauty I really like because of that. Otherwise, I tease my wife. I wish I didn't marry a mathematician, but common sense, on the other hand, is, that's somewhat uncommon nowadays. But if you build it up on it, it will serve a lot good for you, both technically and socially. Now here are the various limitations before you have to satisfy these, before you develop a design based on the direct method. In other words, the direct design method I'm going to talk about is not applicable if these limitations are not satisfied. What are the limitations? Example, ratio of span to width ratio. Each span should be within this. In other words, if I have 3 spans, for example, one span is 30 feet, the other span we tolerate it if it is 35 or 40 feet, but we don't tolerate it if it is 55 feet. Yes. It won't work. The method won't work. That's what I mean by tolerate. All loads are uniform in gravity, not good, not valid for horizontal. For panels, relative beam stiffness in 2 directions is in that range. 0.2, between 0.2 and 5. So keep that in mind. Find factored statistical moment. M0 in each of the 2 perpendicular directions. Distribute M0. What is M0? I will define that in a minute. To design with the cross section from M0 plus and M0 minus, positive and negative. Distribute the moment to column, middle strip, and the panel. These are all, I will relate this in terms of an example problem, okay?
M0 is the moment before the redistribution.
Yeah, all these are before redistributions only. Yeah, we are not even accounting for any redistribution in, maybe I should overly emphasize. The steel reinforced frames or slabs allow some redistribution, 0 elements for redistribution when it comes to GFRP reinforced. Why? There is no yield value. So it's made it very, very clear. All right. So proportion the size, and based on that, so design, these are the different steps. I'll go through them tomorrow, but these are very standard. I did talk about this in one form or the other, at one time or the other. I will reiterate them tomorrow when I'm going to wrap up the session with the design of two-way slab. So these, I no need for me to read it. There is a second method known as the equivalent frame method, and this more rigorous method than the direct design method, differs from DDM in finding longitudinal variation in bending along a design frame. Meaning what? That statement in the parentheses implies that DDM was only good if it were a uniform load type thing. I said that.
Yes.
But here we can have concentrated loads or triangular, whatever loading and it is still valid. That's what it means.
And the lateral loads are.
Oh yeah, lateral loads are allowed in this method, not the previous one. The reason why it is allowed is because it is a computer-based modeling. Initially. Moments are distributed at critical sections by the elastic analysis. No limitation on the dimensions and loadings. You remember we said in the DDM we have to have this, we have to have that. You cannot have more, you have to have at least 3 spans, and spans cannot exceed 30%. All those here we don't have, because that's a computer base. The DDM you don't have the variability, luxury for moment of inertia. Here you have. Effect of lateral loading can be accounted for in the analysis. Statistical moment need not exceed m0, which is required by the direct. So this is how I told you, they gave you the analogy of tug of war. That's essentially what this amounts to in mathematical terms. And the KC, this is all defined. This is how they have the carryover factor. This is all the higher order analysis. So now we will start tomorrow the design utilizing DDM for a two-way slab design, and this is the material given to you. And I want to make it very, very clear. This is the only one example, only one out of the 14 that I copied from that book. And then I asked them before I copy, because I thought I may be violating the patent, or not patent laws, whatever the law, copyright laws. So then they said, no, I'm not violating as long as I said this. That's why I said what I said. You got it? Yes. I need to alert you. Manual 723. So I will discuss that tomorrow, along with fire-related issues. So this is about 3:40 right now. Oh, 4 o'clock, sorry. I'm not allowed to. I don't know how you are withstanding. We are now in US we're going into what they call micro-credential type teaching. You know what that means? That means we spoon feed them, we give 10 slides, ask questions. So these 10 slides or whatever, 8 slides, 12 slides, whatever, should not exceed 10, 12 minutes. You know why? Attention span. Then we ask questions. Then we go to 10 more or 12 more slides, ask questions, like that. So we are trying to engage. Suddenly, I thought I'm supposed to convey the knowledge, right? But with all this, suddenly I'm going to be turning out myself to be an entertainer, not a teacher, Otherwise, they're saying I'm not I'm not keeping the attention of the audience unless I'm not a Johnny Carson, you see. So.
So in the classes, are they allowed mobile phone and these things, are they allowed?
No, I don't. I'll say get out. I can be. No. Some are little lax, but they know it too. Who is going to kind of let go? Who don't let? They know. The student play a game with you, and they know up front, and we know too. I haven't been born yesterday, right? So I have seen all the characters. So, by and large, they're good. I don't want to say, but there are always a couple of people that want to challenge you in a wrong. I don't mind you challenging me in a technical sense, but don't you try to challenge me in terms of social behavior.
Sir, I have a doubt. In the design of column, can we go to this slide?